Hello, everyone, and welcome to History Now, the Future, where we talk to interesting people about some of the most pressing issues of today while using history as our guide and the future as our destination. My name is Corey Bradford. You may know me as This is Corey from TikTok. And today I'm actually going to be talking to someone who is also very popular on TikTok. He's actually got a very interesting story. So he started out his career as a D1 athlete, college football player for the University of Kentucky until injury put him on the sidelines. Now, most athletes, when they're sidelined by injury in that manner, they usually look into maybe being a coach or maybe doing broadcasting, sports journalism, something like that. But my guest today took a very different route. It was that injury that showed him he had a love for something very different that most athletes aren't very interested in. And that's the universe. Physics, science, space. Yes, my guest today ended up completing his dual bachelor's degree in physics and astrophysics from the University of Cincinnati. He is now a PhD student at UCLA, one of the best schools in the country. And he also studied physics at the Harvard Smithsonian Center for Astrophysics, as well as NASA's Goddard Space Flight Center. Welcome to the show today, Dakotah Tyler. Thank you so much for being with me today.
Yeah, thanks for having me on. And that was a pretty astounding introduction. Hopefully I can live up to that. That's great.
Thank you, man. First and foremost, I just want to say you popped up, some of your content popped up on my TikTok page, several months ago, before even either of us was following the other person. And I just remember being like, wow, first of all, the guy knows what he's talking about, but he also has a very different background from most of the people who study this. But what's one of the things that really made you gravitate towards the scientific side of things?
Absolutely. It was and so it really is closely tied with the whole injury and not really being able to play anymore, because during that time, obviously I was like very down. I was very depressed because the only skill set that I really felt that I have, the way that I saw myself being successful was through playing football. And then when you don't have that, it's like, okay, so not only do I not have the one thing that I know I was going to do for the rest of my life, never mind that the average football career is only a few years anyways, but also I didn't really know what other things I was interested in because I never really focused on anything besides sports. And I think it was the perfect intersection of me being like depressed and not knowing what I was going to do, just watching these documentaries, these astronomy documentaries, finding out that there's all the other stars have planets, there's trillions of galaxies that each have hundreds of billions of stars. I think it like lifted me up, sort of metaphorically at a time when I needed it. And it gave me a new goal, like a new thing to set out and go try and accomplish. So it really served the kind of like dual purposes when I first started, both making me feel better, like spiritually, emotionally, like lifting up my mood, and then also giving me a new goal to focus on.
That's really cool. So talk to me a little bit about that transition. So you were a college football player. You went to the University of Kentucky. I'm originally from Alabama, by the way. When you're raised in this, area, you spend your entire life really knowing a lot about football, especially college football. So you was going to
Yeah.
the University of Kentucky. What position did you play? Was that always a dream of yours to be like in the NFL, to just do that for your life?
Yeah, growing up, I always played sports. And as I got older into high school, football was the one that I enjoyed the most, and it was the one that I think that I was best at. So focused on that. But it was always, like a childhood dream to play in the NFL. You kind of look up to your favorite players, and that just sticks with you up through high school. And if you're fortunate enough to get a scholarship like I was, and ended up in Kentucky, and we played Alabama, and Alabama used to dog us. Alabama, this is basically like playing the Miami Dolphins. This is a completely NFL player-ridden team, and yeah, so I mean, it was definitely a lifelong dream, and so much so that there was really no backup plan. There was really no like other thing that I knew at the time that I was interested in when I got hurt. That's
It's interesting because something like science, physics, this is really complicated stuff. And a lot of people who go into that they grow up with that love for that or just a desire to learn more about it. But it sounds like with you, it's a little different. It sounds like you grew up with a love for sports. And then when this
Yeah.
injury happened, you started watching these different documentaries, these different things about the universe. And that kind of sparked your interest. Is like, wait a minute, what is this all about? And that's kind of what pushed you in that direction. So talk to me a little bit about like, you've gone into it a little bit, but like your state of mind, like, so you get injured, but if you don't mind me asking, what type of injury was it?
It was an ACL, and
Oh,
which is not, that's not these days, that's not that serious of an injury. A lot of times guys are back within a year, like less than a year even. But, for me, when did this happen? This was about 12, 13 years ago. I like developed some complications while I was rehabbing and ended up tearing my meniscus a couple more times and then developing like some problems with my patella tendon. So it was really like everything just went the wrong way during that process and ended up, getting to the point where at my new 100% was not high enough to train at the level that you need to train at to be a high level athlete. So it was a knee injury.
okay. So after you have the injury and you start to pivot and make this discovery of that, you find that you're interested in astrophysics and science. What is the process? Like, do you transfer? I know you went to University of Cincinnati. So
Mm.
what was the process? Because I remember reading in your bio that you went to a community college first before you
Yeah.
made that full transition. So what was it like, the transferring of it? And were you kind of like intimidated about like, man, this is a totally different thing I'm going to have to learn from scratch. So how am I going to be able to do it? It's going to take so long to actually get fully educated in it. What was that process like?
Yeah, all of those things occurred. So I'm just watching the documentaries. I say, oh, this is something that people do. Like you can become an astrophysicist. This is a job that you can have. And I didn't know the first thing about what that looked like. So I literally picked up the phone and called a physics department at a university and asked, like, how do I get into that program? Because I'll have a bachelor's, because I did graduate from the University of Kentucky, but they said that I needed like multiple years of calculus. I needed multiple years of foundational physics courses. So basically, I was going to have to do an undergrad degree and redo a bachelor's. And I wasn't even qualified to get into a bachelor's program because I had never taken like algebra, trigonometry. Like I really kind of had to go back to some of the high school level foundational mathematics courses. And that meant that I was going to have to start at community college. So that's kind of how I mapped out everything that I was going to have to do. I basically started from, the age of math that most people probably learn when they're like 15 or 16, something like that, and went through the entirety of the education. It'll end up being 10 years, I think, when I graduate next year with my PhD. And that was something that held me up, especially at a young age. You're 20 years old, looking and saying, hey, you can do this thing, but it's going to take you 10 years. It's like that is like a lifetime. That's literally like a lifetime. And that was something that I at first did cause me to hesitate, but eventually I kind of like realized, all right, so the reason that I'm playing football is because I love this. Like I want to do this as a job because this is something that's fun to me. Training to me is fun. The hard stuff is fun. I love to dedicate myself to it. And I want to have that sort of career. And when I'm laying on my deathbed, hopefully at age 80 or 90 or whatever, I doubt that I'll look back and wish that I hadn't spent an extra 5 or 10 years, at the beginning of my adulthood, getting this extra training so that I could study the thing that I love to do for the rest of my life. But I could see myself, aging and then looking back and wishing, dang, what if I had, when I had more free time and I had more energy, what if I had just went and saw if I could do it. Okay, and you're right, it is hard. That's part of the reason that the schooling takes so long. Like there's a lot of information, there's a lot of technical skills that you have to develop before you can, accurately make conclusions about the universe.
Absolutely. I mean, that's a great way to put it. One thing I think is very interesting about your story is Do you feel like the discipline that it took to be, a D1 college athlete, do you feel like that helped you when it came to the discipline that it takes to, sit down and study something like calculus for as long as you have to, make the good grades, to keep advancing to the next level, to get all the way to like, being a PhD student at UCLA, that's not a small feat. Like that takes a lot of dedication just to get to that point. So do you feel like that discipline that you learned and by the way, I love on your website where you say from the gridiron to galaxies. I absolutely love that. That would make a great title for your book one day.
Yeah.
But do you feel like that discipline that you learned there on the gridiron helped you in the classroom?
Yeah, absolutely. I think that in sports, you kind of learn early on, you learn a lot of failure, you learn a lot of how pushing yourself is actually good, how like the pain and the negatives that you feel from losing games, from, failing in workouts is actually building towards something better because it's helping you improve, it's making you stronger. And that is training that there aren't a lot of ways to get, honestly, outside of sports for young people. And everybody goes through this as adults, right? Like everybody goes out into the real world and then you like don't get the promotion or you don't get hired for the job or you mess up, on a project or something like that. And I do think that having that initial training in sports and just that mindset of, okay, I bombed this test. That doesn't mean that I'm going to fail the class. That doesn't mean that, I can't go on and still go study planets or whatever it is that I want to study. It's just a matter of practicing more, fixing the mistakes, seeing where I went wrong. What is the fundamental understanding that I have in math? Like, what is one of the rules that I keep forgetting that's causing me to not be able to integrate this equation properly? Or, whatever it is. And just seeing the positive feedback of taking that approach, really just like a growth mindset where you don't see failures and setbacks and challenges as deterrents. You see them as like stepping stones and positive indicators that you're on the right track to do the thing that to accomplish whatever the goal is that you want to have. So I definitely attribute my mindset in those difficult and challenging times to one that I developed and kind of honed during my time playing football, for sure. For sure.
Yeah, definitely sounds like a lot of perseverance is necessary for either of these paths that you've taken. And it sounds like you have a lot of that in your wheelhouse. So what is your specific area of study when it comes to astrophysics?
Yeah, so I study what are called exoplanets, short for extrasolar planets. And extrasolar, these are just planets that are outside of our solar system. So, when you look up at the sky at night, you see all of these stars. Depending on where you are, you probably can't see too many. You can see like 14 here in LA. But all of the other stars, they also have planets. The our solar system has 8 planets. Other stars also have multiple planets, and they're not like replicas of the planets that we have. It's not like they have their version of Mars and their version of Earth, their version of Jupiter. The planets, they vary wildly. Like a lot of the planets that we see are actually nothing like the planets that we see in our own solar system. Some of them are similar, some of them are like a Jupiter but super close, so close that it orbits in a couple days. Some of them are Neptune-sized planets that are on 10 or 20-day orbits. Like there's literally just this incredible distribution of planets, almost as many ways as a planet can possibly exist. Basically, we find out there when we look in the galaxy. So that's what I study. I'm an exoplanet researcher. I do observations. So I get on the telescope, get the observations for whatever kind of experimental question that I'm trying to ask. And then there's a lot of coding and data analysis. Obviously, you write up your results when you get those. But yeah, exoplanets is my specialty.
That's like super fascinating to me. Like that's really interesting. So you said there's a pretty wide distribution of the different types of exoplanets that you see out there. Do
Sure.
you do you this is something I've always been very interested in. Do you tend to see more on the side of like the gas giants, the Jupiter types that really wouldn't be able to support, at least in our understanding of biological life, probably wouldn't really be able to support life like that, versus a planet that is more kind of like like an Earth-like planet or a Mars-like planet that has a more solid surface that could potentially one day see either humans travel to it or could also have life itself. Like, what is the like? Do you see more of the gas giants or more of the planets? Like, or I'm assuming you probably see more of the gas giants or something similar to that.
So when you look at planet, really when you think about astronomy at all, what you're probing is like large scale statistics. So let's just say that it's hard to find planets. Like it's difficult to detect them, to like build a detector that's precise enough and put it on a telescope that's been calibrated just right, and then like mitigate the effects of Earth's atmosphere. And it's challenging to find a planet. What you're gonna find is the easiest planets to find. And this is intuitive. A large planet is easier to find than a small planet because it's going to leave a bigger evidence trail behind it, more or less. And so we do find a lot of really large gas giants, and we also find planets that are closer to their stars for the same reason. It's easier to find a planet that's closer because it affects its star more. Planets that are further away are going to have smaller effects, and you're going to have to like look for a longer period of time. You think about the Earth in our solar system. If some alien astronomers wanted to detect Earth using the radial velocity method, one of the most common methods that we use and one of the most successful methods that we use to detect planets, you would have to basically observe our solar system for like over a year because it takes the Earth a year to complete an orbit. And you really want to see the orbit turn over a time or two. So it's like you start to get these unrealistic time scales when you're talking about planets that are as far as the Earth is from the sun or even further. So we have a really skewed data set, a really biased data set towards planets that are probably very hostile to life. Like the easiest planet to find is going to be a Jupiter-sized planet, a gas giant that's right next to the star. That's going to be the easiest planet to find. They're not necessarily the most common, but they were the ones that we found first simply because they were the easiest to find. You see, so when it comes to the planets that we find and whether or not they would be suitable or habitable for life, at this point, a lot of the planets that we find are too easy to find to be that nice for life to evolve. I mean, it's possible that we've come across a planet that has life or something like that, but we just have these limitations in our instrumentation where we're biased towards large planets that are really close. And then we also can't really detect thin atmospheres like the Earth. Obviously we have an atmosphere. You go outside, you feel the wind, you can breathe, all of this stuff. But if you've ever seen a picture of the Earth, our atmosphere is like really paper thin. It's like this very thin white little casing that moves around the Earth, and you can kind of see it when you look at an angle. So by the metrics of people in my field, I would basically say that the Earth is consistent with a planet that didn't have an atmosphere. That's kind of the level that we're at in studying other planets, where we haven't quite gotten to the point where we can sort of like finally assess thin atmospheres. And if we're assuming that life is going to be something like it is on Earth, which is a fine assumption, it doesn't have to be like a limiting assumption, but it makes sense to start with what we know, then we're not really there yet. Like I couldn't really tell you. We've definitely found lots of rocky planets, but just looking at our own solar system, 3 out of the 4 rocky planets absolutely don't have, well, I won't say absolutely don't have life, but they don't appear to have any life as far as we can tell. So that's really like I think the big question that we're building to as we take this step, each step. Like the first thing we do is we find planets, and they're the easy ones to find. And we get a little bit better with our instrumentation, and we find the ones that are a little difficult, and then a little more difficult. And then eventually, hopefully we get to the point one day where we're like spotting planets that actually look like Earth, that actually have oxygen and methane and nitrogen in the atmosphere, but we're just not quite there yet.
That's really interesting. Yeah, and about the rocky planets. Yeah, I don't think Venus is. I don't think too many people are living on Venus right now. It just doesn't seem like it would be conducive to that. One of the things that I've always wondered when it comes to our own solar system is some of the different moons of like, I know Jupiter and Saturn, they all have like tons and tons of moons, and some of these moons are kind of rocky. Most of them are pretty much rocky, kind of like our own moon. So, is
Yeah.
there a method when you're studying these exoplanets? Is there any type of method that you could also determine, if there's any moons, natural satellites that are orbiting those planets, or would they just be way too small to detect?
Yeah, that's so that's kind of the next big thing that people are trying to discover are exomoons, was what we would call them. Yeah, moons that are orbiting other planets. I mean, there's tons of moons in our solar system. Surely, the physics is the same everywhere. So there should be moons orbiting other planets as well. We haven't been able to detect any yet. Part of the reason is because they are small. Part of the reason is because of the nature of how we detect planets to begin with. So the methods that we use mostly are indirect methods. So if I'm looking for a planet like Jupiter, which we know has moons, but it's orbiting, a star that's far away, I don't actually see the planet Jupiter. You can directly image some gas giants, but very few. There have to be there's like a pretty tightly constrained set of circumstances that will allow you to actually snap an image of a planet. But for most planets, it's like I can't see Jupiter, but I can wait to see the effect it has on its star. So as Jupiter orbits the sun also does its own little orbit. Because really what's happening is that the sun and Jupiter are orbiting a common center of mass. But the sun is so much more massive that that center of mass is, basically close to the sun. Now, one way that we could detect Jupiter is by just staring at the sun for however long it takes for Jupiter to do a complete orbit. I believe it's 11 years, something like that, which is a long time. Another way is if we just happen to randomly be lined up in the right orientation, then we could expect that, some degree of Jupiters are going to cross right in front of their stars and just block out a little bit of that starlight. That's called the transit method, and that's the most successful way that we have found planets. But in either of those methods, you don't really probe the space around the planet. You're really just like inferring that a planet is there. So it's hard to detect whether or not that planet has moons. I mean, in the radial velocity method, the sun is doing its own little orbit around the common center of mass, but the mass of Jupiter and the moons is sort of lumped together. It's not like doing something special because it has moons. So this is like one of the current challenges, because I mean, even looking at the moons in our own solar system, they're as diverse as the planets, and there's many more. So it's like there's even more chances for potential life to occur. There's some moons in our solar system that we think may possibly have liquid water and life in them out in the outer solar system. Um, and we have a chance to go to those. I know you said earlier, like planets that we may actually have a chance to go to. We really don't have a chance to get anywhere because everything in space is too spread out. Currently, unless we came up with some new technology that it really blows out of the water whatever we have going on now. There's not. I don't really see it being realistic for us to ever go to another planet. But I mean, who knows? I'm sure there was a time when people thought that we'd never go to space or you could never go to the moon or something like that. But yeah, exomoons are really, really interesting. I wouldn't be surprised if there's more moons with life in the galaxy than planets. We don't have evidence for that, but that would not surprise me at all.
Yeah, that concept is really interesting to me because, like you said, there are moons like of Jupiter and Saturn that we think may have at least some of the things that are necessary for life. Maybe not actually have life on them, but they may have some of the things that are necessary for life.
Yeah,
Now,
yeah.
one of the things right now, okay, so 50 some odd years ago, we went to the moon. And now there's a push to go back to the moon. We know that China and different places like that have been landing unmanned space probes on the moon. India recently did so. So now there's this push to get back to the moon. And
Yeah.
then also a lot of that has to do with finally pushing humans towards something like Mars.
Mm.
So in your kind of estimation based off of just like where things currently stand, what do you think the timetable would be to go to one of those moons of, say, something like Jupiter or Saturn? Like, is that something that's like 50, 60 years off? Is that like a century away? Or is that something you could possibly see happening in your lifetime? Or is the goal just to getting to Mars so difficult that we're still a ways off for being able to go to like Io or Europa or something like that?
Yeah, that's a really good question. So Mars is something that there's still like some technical challenges to overcome, but that does seem feasible. That seems like something that we could expect to happen in our lifetime. One of the big problems going far away from the Earth is that once you get outside of the Earth's protective magnetosphere, this like giant magnetic field that's generated from the inside of the Earth, you are exposed to a bunch of like cosmic radiation, basically just high energy particles that are coming from the sun or from out in deep space that are just always penetrating everywhere. And that's something that is dangerous to be exposed to for long periods of time. It's sort of like, I mean, it's radiation, so it's just a probability thing. You stay in somewhere with a lot of high radiation, the probability increases that one of these particles strikes you in such a way that it like destroys your DNA or something and gives you cause your cells to deteriorate or cause you to get cancer or something like that. So that's a big problem going to Mars. There's also like a problem with being in low gravity for such a long time. Astronauts in space already have to work out for like 2 hours a day or something like that, minimum 2, 3 hours a day, just so that when they come back to Earth, their bodies have not decayed to the point where like they can't stand up. So, going out as far as Jupiter is a huge challenge, and particularly going to the moons is a problem because you can't just approach Jupiter like you approach Earth. Jupiter's it has a much stronger magnetic field, and it gives off like a lot of radiation. Some of its moons outgas stuff into the kind of the orbital area around the planet, and the magnetic field is so strong that it can like ionize some of that material. So, you really couldn't get close to Jupiter. I don't think that you could even land on any of the moons with you know, and it be safe. Like it's just a little bit too dangerous. I guess you could probably come up with the protective suits and protective shielding and that sort of thing for your spacecraft or whatever. So, I wouldn't say that it's impossible, but I wouldn't put any eggs into that basket until I actually saw us put the plan together for Mars and go to Mars and have that be a success, and there's no like giant disaster where something catastrophic happens to the crew or the spaceship or something like that. I think that I mean, but that hopefully that's the direction that we go to, that we get to the point where we can go explore these places. And there's probably, hopefully this isn't like too much of a colonizer mindset, but if there's nothing living on any of these moons or anything like that, maybe there's like tons of useful resources that we could use that are helpful. Like sources of energy. I don't know. The possibilities are sort of endless. Like we find countless ways to use what we have here on Earth. Other planets have a lot of the same stuff, but they also have a lot of different stuff, especially the moons. So, timeline wise, I think I would be shocked if we sent a manned mission to one of the moons of Jupiter in my lifetime. I would be shocked. I wouldn't bet on that. I would bet on Mars though. I would bet that we get our act together on Mars.
Yeah. Yeah. Mars seems more feasible. But even, with those moons, like you said, with the resources, it may just make more sense to send unmanned missions to
Yeah.
those instead of trying to risk sending a human being there, because it sounds
Absolutely.
like the challenges you just stated are going to be very insurmountable. Like I don't know if we're going to be able to overcome that anytime soon. So yeah, it may just make more sense to just send the robot, send the
Yeah.
AI, and let them do the dirty work.
That's
But
what we did with Mars, right? We have
yeah, yeah.
sent rovers to Mars. We sent seismographs. Like that's what we've done, and we've learned a lot about it. And there is like a level of uh, scientific progress that you're gonna be able to make with a person that you can't just make with a machine. But so it would be better to send a person. But yeah, I mean, off the bat, we should definitely send some robots before we send people. Now there's a mission. The Europa Clipper mission is going to Europa, which is one of Jupiter's large moons, and we believe that there's a layer of liquid water underneath like this thick sheet of ice. And that's really interesting because the radiation that I mentioned around Europa would be a problem for anything on the surface. And it doesn't really have that an atmosphere. It's kind of too small to have a significant atmosphere. But you could imagine this thick layer of ice sort of being protective against the oncoming radiation.
It seems like a very interesting time period, because you're telling me that we've got missions going to Europa. A couple of years ago, we changed the course of the direction of an asteroid by crashing something into it, which could
That was really
really,
interesting. Yeah.
yeah, and that could like really save us one of these days if one of these asteroids gets
Yeah.
a little too close to Earth.
It was that's really interesting because there was a bit of a surprise there. So I think the way that I have always thought about asteroids is that they are these like big rocks, big boulders. Maybe they're the size of a baseball or a car or a house or a mountain or something like that, but that they are solid rocks. And what they found out with that DART mission, where they kind of looked at there were these two asteroids that there was one that's bigger and one kind of orbiting it, and they wanted to see if they could adjust its orbit because that's what we want to do if we had an asteroid coming towards us. And when they impacted, they realized that it's not this solid like rock that you can kind of push off course. It basically was a giant pile of gravel. So, you know, it didn't really do exactly what we hoped that it would do. Like it still has like a center of gravity and a center of mass, so you can mess with it. But that was like a huge problem because imagine sending a projectile to knock an asteroid off course, and all that happens is you split it literally into like 50 million pieces that are still coming your direction. So I think that was a bit of a surprise.
I think there was recently some movie about that, like where they blow up the asteroid and it just turns into all these different pieces that just start randomly hitting different parts of Earth. It's like, oh, well, we just created a much bigger problem here. So that's
Right.
really interesting. But with all these different things that are going on, we had the first photograph of a black hole in the last couple of years. You just don't seem to see as much excitement for a lot of these discoveries the way you did, like when we went to the moon 50 something years ago, or even space shuttle missions. When I was growing up in the 90s, there was more excitement, it seems like, around that than today. What do you see as your role as a scientific communicator, as someone who has just illustrated in the last 30 minutes that you know what you're talking about, a ton of what you're talking about, and you're very good at communicating these messages on social media. What do you
Mm.
see as your role with getting more people interested in these discoveries, interested in the possibilities? Because a lot of the things, like you said, that we're doing now, they go so beyond things like going to the moon and stuff like that we did 50, 60 years ago, but we just don't seem to see that interest. So what do you see as your role there?
Yeah, that's a good question. I guess I see my role a couple of different ways. One of them is to get young people interested who maybe like didn't see themselves as scientists, or they don't see scientists who they feel like that they resonate or can relate to. Because I definitely think that was me when I was younger. I saw myself easily having a professional sports career. Never would have ever seen myself as an astronomer, an astrophysicist. So that's a part of it. The kind of the thing that you're saying, like it's cool, like science is cool, like information is cool. Being curious, wanting to learn things are fascinating. How everything, I mean, in your room right now, there's probably a dozen things that would be completely fascinating to figure out exactly how they worked, and kind of just like spreading that and being myself with that, and like letting it be okay. And then I think another thing that or another role that I sort of see for myself, aside from just like getting young people interested, is generally spreading the scientific knowledge. I think one of the reasons that you hit on something interesting, that it doesn't seem like there's as much hype and excitement around space as there used to be. And I think that there's like a lot of people don't even think space is real. They don't think that the Earth is round. They don't think, like, it's a significant percentage of people that sort of have fallen into this conspiratorial way of thinking. And it's, if you, and I believe that if everybody had a better grasp of like scientific critical thinking, and in that scientific sense, then it actually makes the world a better place. Like, people have a better way of thinking about information. If you understand why we can trust those images of the black hole, for example, and you understand like the methodical process, all of the checks and balances that occur in that entire endeavor, then you have a better foundational way to think about your life, like to think about the things that you do, that you want to do, to form your opinions about what you think is right or wrong, how you assess information that you're getting from politics, or politicians. It's just a general increase in scientific literacy, I think, is good for everybody. And I think that that's like another positive impact that I can have.
I think you make a ton of sense, as in like your role as a scientific communicator is really to just get people to have that critical thinking lens, to be able to actually assess these things with
Yeah.
just a logical point. Because like you said, I mean, we got people who, obviously there's so much mistrust in science these days. People who don't believe we went to the moon, which I know that's very frustrating for you as an astrophysicist who studies these things on such a critical level. But also just imagine like an actual, there's a few men alive that actually did go to the moon. And it's like when they hear that, I mean, all that sacrifice and time they spent doing that, and people don't even believe they actually did it. And so that's insane to me. But I also think that it is, it's basically on the scientific communicators, the actual scientists, to do the best job they can to communicate these things better to people who simply
Mhm.
just don't understand, where they're coming from, and don't understand, like, basically, because like the difference between me and you is like, I do the history thing, and so like I have the same thing where people are kind of like, well, I don't believe that this actually happened in this year. And I'm like, well, we have a lot of evidence to
Yeah.
show that it happened.
Mhm.
And in history, a lot of things can be easily fabricated. And, sometimes the winners write the history that we learned in school. But with science, you guys have to actually show, like, the act with the scientific method and with actual physical
Mhm.
research, you have to actually show your work. And that's why you would think it'd be a little easier to get people to believe you and trust you, but a lot of people just don't understand the work. They don't understand why what
Yeah.
you're saying makes sense.
Yeah.
Um,
Yeah.
and is that something that you feel like could just be improved by maybe just like a language? It's like just the language of how scientists kind of talk to the public.
Yeah. Yes. So there's a couple things. One of them is that there is this like huge, huge mistrust that I think is really rooted in a mistrust of like the government. And there's a long list. I mean, as a historian, there's a long list of like, atrocities that every government has committed, and lies that they've told to their citizens. And an agency like NASA is a government agency. It's run by the government. And so I see how sort of a naive first glance at a conspiracy or something says, oh, well, like maybe they can't be trusted. And that is a fine way to look at things. But that, like you said, that's the point of science. Like, every discovery that anybody is saying that they have made, there's a paper that's attached to it, and you can go through it. You can go through it and you can see what doesn't make sense to you, like what, and you should be able to recreate these experiments. At the very least, usually the data is available, if you wanted to get your hands on it. If you like really wanted to, you could, and you could assess, what's being said that way. But there's so much misinformation that, pretty much whatever you think, you're going to be able to find a page dedicated specifically to that thing. And a big part of it is definitely communicating it in a way that makes sense. But there's this weird thing that I'm noticing as well. And I think it really stood out to me. I don't know if you saw any clips or are familiar with the Terrence Howard appearance on the Joe Rogan podcast. And
Unfortunately, yeah, I'm aware.
yeah, yeah. And it's this thing that there's this thing that I always try to not do, which is to overload any sentences that I have with a bunch of technical words that people don't know. But weirdly, a lot of times people associate that with the person speaking being really smart because they just know all these words that you don't know. But because you don't know them, you actually don't know if what they're saying makes sense. They could be just doing a technical scientific word salad. And that is oftentimes what's happening. Like I'll hear people talk about the quantum vibrations and manifest, and I'm like, that's not what the Nobel Prize went to. It didn't go, that's not what they showed in the lab. That's not what the paper says. And it's hard to kind of like balance that, right? Where you still need to seem like you know what you're talking about. You don't want to go too far with the technical jargon, but you also don't want to go like so low that it seems like you have a like a middle schooler's understanding or something like that. So that was something that I think was really interesting, that so many people that are saying, oh wow, like listen to him talk, he's a genius. And if you really just pull out a dictionary and put the definitions of the words in line, you're like, what is this is like random. These are random words being generated. So yeah, it is absolutely on, in my opinion, it's on scientists, science communicators to be able to relay that information in a way that's relatable, that's engaging, that makes sense, that's responsible, that's right, that has been like fact checked and is appropriate. And there's not a lot of people really who are, there's a fair number, but a lot of the people who do a lot of science, they're like not into the science communication thing. They kind of like look down on it. It's like a lesser form or something like that of science or communication. Obviously, that's not how I feel. And there's tons of great science communicators, especially on TikTok and YouTube and that sort of thing. Yeah.
Yeah, and that's something I've noticed too. There does seem to be this within the scientific community. It does seem to, like when you're a scientific communicator, like if you're like Neil deGrasse Tyson, or like we grew up on like Bill Nye and people like that. There is this sort of like, oh, they're not real scientists. They're just talking about it. But it's like, no, they actually got degrees. They actually have to do a lot of this work, and they have to understand it in order to communicate it. And I think like them and as well as yourself, one, you guys are actually doing real science in your careers. But two, the fact that you've also spent this additional time to communicate it properly is essential for, like you said, getting young people to discover these paths
Yeah.
for their career and just to improve their critical thinking skills. But also, it's just essential for the public so that we understand what NASA is doing, why they're doing it, what's the reasoning behind this, what's the actual logic behind this. I think it's essential. I think it's absolutely crucial.
Yeah.
And I think they're doing that in places like China and Japan. And I feel like we're kind of coming up short here in America. And so I really appreciate you and the work that you do. One of the last questions I want to ask you is like, well, yeah, of course. What do you think is next for you? I know you said you got about a year left to finish your doctorate. What's next for Dakotah Tyler? Like, where do you see yourself 5, 10 years from now in this field? How do you see yourself moving forward?
Yeah, that's a good question. That's obviously something I'm thinking a lot about now as my time in grad school is wrapping up. And I definitely love doing the science communication. I love that part. That's always going to be a part of what I do. And I like doing the research a lot as well. But I don't like, you get into this thing with research where if you go on to be like a very serious researcher, you sort of don't have as much time to, there are some people who I'm amazed by their time management, how they're able to like balance doing both at a really high level. I really think that where my passions lie and where my skills lie is like more doing research in a minor role. I have some collaborators that I'll always want to continue to work with, but finding the sort of maximizing the ways that I can deliver the science communication. So that'll be like in writing. You mentioned a book earlier. Like there's, of course, I have a couple ideas for books and some ideas that I'm working on. Creating videos, maybe starting a science podcast where I'm going around and talking to just scientists in different fields. I have a lot of collaborators. I have a lot of colleagues and friends that I've met just on TikTok that also do their own science. And so I also do a lot of public speaking, like planetariums and speak talks to kids, keynote talks, and that sort of thing. So I think just for me, it's maximizing all the like getting as good as I can in sort of a jack of all trades in specifically science communication. All the different ways that it's done. That's my big focus. I'll also apply to some postdoc positions, which after you get your PhD, it's common to get what's called a postdoctoral position, which is it's like a temporary position that usually lasts between 2 to 3 years, where you're doing more research, but you're doing it more independently as opposed to kind of working directly under an advisor. You still have an advisor, but you're kind of taking your next step to that next level. And who knows, like maybe if I get a position like that and things go well, I'll want to continue going on in that direction. But I think for me, where I really feel called in like what's authentic for me, the thing that feels like my purpose, it's maximizing my time doing the science communication, however many different ways I can figure out how to do that.
Well, it's very, very important work, and I really appreciate it. Every time I see one of your videos on my page, I always stop to listen and stop to hear it out, because I'm always very interested in that sort of thing. But also, you deliver it in such an interesting way. So definitely appreciate your work. Just for the people listening, tell them how they can find you. What's your handles? How can they find you on the internet?
Oh, for sure. So I have a website, www.dakotahtyler.com. If you want to get in contact with me or something like that, book me for a talk or anything, you can contact me on there. And then on all socials, it's at DT Star Kids. So TikTok, Twitter or X, Instagram. I have a Facebook page. It's all DT Star Kid.
Awesome. Dakotah Tyler, thank you so much for being with us, man. Take care. I really appreciate the conversation.
Yeah, thanks, Corey. Thanks for having me, man. It was great talking to you.